changes in atmospheric circulations over Europe, given a warming world, warming also Europe. And then we can start with the fact that, or questioning what is actually a circulation type or a circulation pattern. We often hear terms like circulation types, pattern, large-scale weather types, or even weather regimes. The difference mainly is that weather regimes usually relates to 500 hectopascals data. That's how usually they define them. Whereas in my case, or for this purpose, we define or use the term of a circulation pattern or a circulation type based on mean sea level pressure data, which is surface data. And that means we are using synoptic surface atmospheric patterns. And this not only is important because we can derive from them things like high and low pressure systems, but also we can infer things like wind direction, wind speed based on pressure gradients, but also other hidden features like troughs and ridges that have been very important, especially in the past when forecast was first done by taking these maps and drawing them and trying to predict what was going to happen in the next coming days. So what we work is on grouping these patterns, and the question is why to group these patterns, where, as we saw, they clearly influence things like wind speed, wind direction, but they also influence things like precipitation. So there is a clear relationship of where these patterns influence precipitation, like low pressure systems usually affect precipitation, whereas high pressure systems do not usually favor rainfall. And they also influence things like temperature and moisture advection. So depending on where the air mass is coming from, how the circulation is taking place over a region, then they influence these atmospheric variables. But these patterns are usually more important, more dynamic over the mid-latitudes compared to the tropics. So based on this statement, we take one method to classify these circulations. There are several methods available to classify patterns, but one of the most classical ones is the land weather types, or in this case, the automated version, which is called the Jenkinson and Collison. And what we took this method and we converted it into a Python package that makes life easier, as I would like to have founded myself at the beginning of my PhD. And as we see, there is this area over the tropics where there is no data because we cannot classify the patterns there. The classification doesn't do a good job. The pressure gradients are too weak to classify. And we see we have 11 circulation types which mainly relate to C and A, for example, cyclone, A, anticyclone. The other correspond to the wind directions, right? So if we see here, for example, we have a high pressure system, and here we have a blue color, which corresponds to an easterly. It's practically a high pressure system just circulating like this, right? So we can derive the sectors of these circulations. And then you can actually access this Python package. I just warn you that if you come across some of these things, don't click on them, you might know that that's dangerous. So one of the ways is just click, install GCA class, but you can also see this further on the poster. And I will not go into detail, but you can ask me later more details. So we classify the circulations like that. I'm going to describe some of the basic, more known circulations. Like the westerlies, for example. If we classify the westerlies, we saw that they influence the day-to-day influence on precipitation, for example, but they also can go and extend their influence on the season, on the seasonality or on the seasonal time scale. As we see here, the westerlies are mainly confined to the mid-latitudes, and they move northern or further north or south, depending on the season. And because they mainly influence the advection of humidity from the ocean, they are a strong modulator of precipitation for Europe. And we can see that here, if we take a look at this graph, and if you focus on the brown and blue colors, brown color would mean that every time there is a circulation, a westerly is happening, it doesn't rain, right? Whereas the dark blue means that there is always rain happening when a westerly takes place. So we see that mainly over the western part of Europe, westerlies are a strong modulator for precipitation. usually sometimes even responsible for 20–30% of the precipitation that we observe over these regions. And the other pattern that it's always also well known is the anticyclonic. So this would stand for the anticyclonic centers, which is how we derive them. And as we said before, these are usually not related to precipitation. And we can prove that by looking at this dry day likelihood map. And we see that practically there is no precipitation associated with these patterns during their occurrence, except over some mountainous areas because of forced convection over those areas. And lastly, but not less important, the easterlies. And as we see, the easterlies are mainly confined to the tropics. That's what they are known as the trade winds, or the easterlies over that region. And even though over Europe, they are not very, they don't take place very often, they can actually be responsible for some events like droughts, heat waves. I mean, they can be associated to these events during their occurrence during summer. And we see that the easterlies, for example, practically are not responsible for precipitation, or more like they are responsible for dry days over Western Europe, right? And there is evidence that some of these circulation types, like the anticyclonics, the easterlies, and southeasterlies, are linked to an increased summer drought severity in Central Europe. And based on this, what we wanted to do is see what's the future scenario for Europe based on some of these circulations. So what I wanted to do is a quick, small review of some of the recent findings based on circulation types for both seasons, and to see how do they match with our findings. So at the moment, we know that we will expect drier summers over Southern Europe, for example, whereas winters will become wetter, especially in Northwest Europe. And one of the issues is that the projected changes in the regional precipitation also arise or are responsible due to changes in large-scale atmospheric circulation. So doing a quick review of the winter, for example, the projected changes say or mention that there is a likelihood that some of the NAO plus events over Europe might tend to increase. However, we have to be careful with this conclusion because there is some intermodal disagreement and biases that still have to be taken into account. However, there are signals for that, meaning that we will have more favorable conditions for milder and wetter conditions over Northwestern Europe. There is also the tendency for more winter patterns associated with cyclonic and westerly types, which therefore will bring more moisture or will increase the moisture advection towards Northwestern Europe. And that means that there is also an increase in the risk for floods over this region, or precipitation, more floods, and this enhanced westerly transport of moist air. And lastly, well, now I feel very not sure about showing the PDFs after the first presentation, but we see here, for example, that a doubling in CO2 over Northwestern Europe would lead to more precipitation, for example, in this case. And the last thing that we see or we can rescue from the literature is this increase in mean sea level pressure on 500 hectopascals over the Mediterranean. So if we have those things into account and we remember them, so this increase in westerlies, more moisture transport, and the increase in anticyclonics over the Mediterranean, and we see if we can pick up those changes in our conclusions using our method of the surface circulations, we have here the changes. What we do is we take a chunk of the present and the future. So 1950 to 2000, and 2051, 2100, using a high emission scenario, so a worst case scenario in the semi-peak global climate models using 22 global models, right? So we see here is just the changes in frequency related to one of these circulations, so the westerlies in this case. And red colors meaning an increase in frequency, whereas blue colors would mean a decrease in frequency. First thing that we can notice here is this increase in westerlies over Europe. Whereas here, just for visualization purposes, we have the changes of precipitation. It's just whether there is a positive change or a negative change in precipitation within this circulation type. So we see that it seems that in the mean of the global climate models, an increase in westerlies would directly, in theory, lead to an increase in precipitation if we see the dotted area. And that seems like the story is very congruent, no? Westerlies increasing, more moisture, than precipitation increasing. But the story is not that simple, and it seems like there might be other factors probably influencing these changes in precipitation, not only the circulations. We see, for example, the anticyclonics. If you remember from here, anticyclonics increasing, westerlies increasing, and we see that also when we pick up these changes in anticyclonics. So anticyclonics increasing over the Mediterranean, which would help with the fact that the Mediterranean will be becoming drier in general. And there is also a precipitation decrease. However, if you see here, where it seems like the anticyclonics are decreasing, but precipitation is also decreasing. So the relationship is not direct. So this deserves further investigation on how the circulations actually influence things like changes in precipitation. And then we take a look at the summer, and let's see what's happening in the summer. We know that summer is becoming drier, especially over Southern Europe, the Mediterranean especially, and probably a bit wetter over Northern Europe, but not too much. So some of the conclusions point that there might be an increase in anticyclonic situations, for example, west of the UK, and that they look more like an Atlantic ridge situation. So an Atlantic ridge situation would mean decrease in precipitation, mainly over, they influence things like droughts and heat waves over Central Europe. And we see also in the PDF that this will lead to a shift towards drier conditions in the Atlantic ridge situations. Another conclusion is a weakening of things like the Central European Eastern high pressure system and the Scandinavian low, which would lead to an increase in easterlies over continental Europe and a weakening of the westerlies. So, and we saw before that westerlies are mainly responsible for bringing humidity to Europe. What would happen in this case? Then now the air masses are bringing drier and warmer air from the inner continent during summer, which in theory would actually also increase the severity of droughts in Central Europe, which I mean, some of the links have been already found to these changes. So if we remember this, increase in easterlies, weakening in westerlies, that's what mainly we find in the literature, or one might agree, one might say cherry-picked to agree with me, but not really. We will discuss this. And we see the changes in the westerlies, for example. Now we see the opposite story compared to winter. Westerlies properly weakening over Europe, and precipitation also decreasing inside the westerlies. In northern towards the north UK, etc., the westerlies seem to be increasing, of course, because there is a shift towards the north of these conditions. And if we remember, the easterlies seem to be increasing, and we do that with our circulation types, we get the signal. Here we don't have a multimodal agreement hatching, but usually we find good multimodal agreement above 80% of the 22 global climate models. And we see that this increase in easterlies would actually, in theory, lead to an increase in precipitation. That's not what we expected. So there might be other dynamical, thermodynamical, and other factors that need to be studied to better understand how these actually circulations influence precipitation, not as they are supposed to, right? And lastly, we also saw that there is likely an increase in anticyclonic situations over west of the UK. So if we place an anticyclonic here, of course, this would lead, given the circulation, to more easterlies over Central Europe and weakening of the westerlies, which would all combine lead to more dry situations over continental Europe, given these circulation changes. However, just to conclude, there are still many challenges related to this. Multimodal agreement still is not 100% accurate. There are uncertainties related to Arctic amplification, upper troposphere tropical amplification, and things like the stratospheric vortex also that have to be taken into account. we have discussed further how these circulations actually influence precipitation during summer. And some of these detailed results are available in our preprint at the moment the article is under review. And we have, for example, done a decomposition to see how these changes in precipitation can be actually attributed to the frequency changes or to other factors like thermodynamical, dynamical changes, etc. And if you're interested in the details, then I invite you to take a look at the preprint. Comments will also be very welcome before the final version hopefully goes through. And I think I am just on time. Thank you.
Thanks, Pedro, for being on time. We have time for a few questions.
Hi, Pedro. Thank you very much for your talk. Very interesting. I was wondering, can you separate between changing the frequency of occurrence and changing the persistence of a particular weather regime so that you can tell more about the changes that you're seeing?
Could you go again with the question? Sorry.
Right. I mean, you can have a particular weather regime that happens more often, right, in the future. But it can be just because, it happens, I mean, one day and then shifts to another weather regime, or it actually spends more time in a particular weather regime. So can you separate between this persistence and frequency of occurrence?
Yeah, definitely we can, because we derive a time series of these patterns. Usually the data that we input for this is daily mean sea level pressure data. So we could actually do it and do another further study on how actually the persistence might be changing. But at the moment we didn't, and we just look at the seasonal frequency of the patterns. But we could, yeah, the data is there.
Other questions? Niklas, do you have questions on chat? No. Maybe I have one, Pedro, as a transition to the next talk. I know you've been able also to compare the historical trends in the frequency of those circulation types with different reanalyses, but it was focused over Central Europe. Have you been able to widen the perspective over the whole European domain? And have you seen any evidence of models underestimating changes?
Yes, in our first paper, we did an evaluation of only like Central Europe, as you mentioned. Now in this second paper, there is an evaluation of the whole Europe, of how the models actually represent the circulations. And there are biases, especially in the zonal flows, like the westerlies. It has been generally reported that global climate models do not do an amazing job in representing these circulations. So we have seen that, and some of the models that perform badly are also incongruent, like IPSL models, and the best ones usually being the British and HATHEM, MPI also. So yeah, there is an evaluation of this in this current preprint.
Okay, thank you, Pedro. Another question, Niklas?
Yeah, not in the chat, but I would like to ask you. I mean, first of all, I cannot say it enough, like really awesome animations that you have. I really love them. Beautiful visualizations. How many of the weather types that you identify, or of these 11 weather types that you have for Europe, can be very strictly associated to precipitation, to like be it wet or dry, like also like deprived of rain? Because I could imagine that some of them are not super well linked to precipitation and maybe have like 50% dry, 50% wet. Could you comment on that?
Yeah, let's say the weakness of the method is that, unlike weather regimes that kind of take all this variability into account and, let's say, simplify the picture of the precipitation associated, the circulation types might have a change in influence depending on the region. Like over Western Europe, for example, we see that over Scandinavia, westerlies clearly influence precipitation, but as soon as you cross the mountain, the westerlies do not create precipitation because of precipitation just staying on the side where the humidity is reaching. So we can define areas where they mainly create precipitation, but it changes from grid point to grid point when using this method sometimes.
you.